the next Canvas quiz, which is on aldehyde ketone nomenclature. So that'll be open by the time you leave today. It'll be due by next class, so Monday 11:30. It, like the ether one, has a homework available. So if you want to, it's not going to be due, but if you want to get some extra practice on aldehyde ketone nomenclature, you can practice with the homework sheet. There's a key, you can check your answers and make sure you're comfortable with it before you actually go and take the quiz. So, but it's going to be due next Monday. All right. Okay, so let me go ahead and start recording and we can get going. Okay, so where we were finishing up last time, we were looking at the crown ethers. And so what we had said was these are large macrocyclic rings, and the point of them is that they complex metal ions. And they do that through those ion-dipole interactions. And so obviously, the more atoms you have in the ring, the larger the ring becomes. So, for instance, a 12 crown 4 is going to be smaller than like an 18 crown 6. And that tunability of ring size allows you to complex different metals. And so you can see, I think we talked about it last time, with the 12 crown 4, that's going to be the smallest of the crown ethers. That's good for complexing lithium. 15 crown 5, you can get sodium. And then 18 crown 6, you can complex potassium. So depending on the size of the crown ether is going to allow you to capture different sized ions. Okay? And we talked about the purpose of that. Oftentimes this comes about when you're trying to perform an organic reaction, but you're using an inorganic reagent. An example we looked at was if you were trying to oxidize, say, an organic alcohol, it allowed you to use inorganic reagents like the potassium permanganate or a potassium dichromate or something like that. So that's the purpose of them. And that really takes us about to the end of the ethers. Right? So I did want to show you one last thing. This is kind of, this little cartoon kind of shows you how this would work. This is supposed to be a potassium ion. And you can see that the red, those are your oxygen atoms, and all of those are pointing inward towards the positive charge of the ion, and they're just kind of complex there using the oxygen lone pairs to do that through again, those ion-dipole interactions. All right. So we spent a bit of time through the ether chapter, and I was telling you that ethers don't really do a lot of chemistry. They're used primarily as solvents, and that's true, but I don't mean to discount ethers as a functional group. It turns out that they are very important in natural products. They're found in a lot of things in nature that have some really relevant effects for us. So for instance, if you're looking at this compound over here, this is called epopholone. You'll notice you have the epoxide up top. This is an anti-cancer agent, and it turns out that if you don't have the epoxide there, it loses its bioactivity. So that epoxide is really quite critical for it to retain its anti-cancer activity. If you look at this one over here, this is a natural product that's called monensin, and you'll notice that you've got a whole bunch of 5- and 6-membered ethers, ether rings. And it kind of behaves as a natural crown ether. So if you notice, you have kind of a hydrophilic or polar side where all the oxygens are pointing in, and then you have a very non-polar side on the outside. And that's really key to its activity. What this does is it complexes metal ions much in the same way that a crown ether will. and then because of its nonpolar exterior, it allows it to kind of seep through cell membranes. And these act as natural antibiotics. So they allow the molecules to kind of go through the cell membrane carrying ions with it, and that creates a massive charge gradient which ultimately ruptures the cell membrane of bacteria. So, and then the last one I have on the list is my favorite. This is called Taxol, and it is it's another anti-cancer agent. It's used a lot in breast cancers. But you'll notice within this very complex structure, you have this four-membered cyclic ether there. And so just to kind of show you that while we don't do a lot of, think about a lot of reactions involving ethers, they are very prominent in natural products. And this structure has a rather interesting side story. It is really kind of mesmerizing in its complexity, but they don't, when the drug is marketed, it's not like people do what's called a total synthesis on it. You know, you don't start from scratch and build this. You can, it's been done, but as you would imagine, it is not a trivial task. I think it requires something like 65 synthetic steps to build it. So what they've done, or the way they get enough of this material to market and sell, is it actually, they can extract an advanced intermediate from a particular tree known as the Pacific yew tree. They grow groves and groves of it up in the northwest coast on Oregon and Washington. But so they are able to extract kind of an advanced intermediate of this from the tree, and then the chemists kind of decorate the edges and get it ready for market. But it was kind of interesting that when this drug was developed, they started developing it in the 60s or 70s, and it caused a real rift because the pharmaceutical company that was developing it needed the yew trees, you know, because they needed to get the advanced intermediate so they could make enough of it to put into clinical trials. But then the environmentalists got all over it because there was some owl or something that lived in the yew tree. I can't remember, but anyway, it causes big stink between the environmentalists and the pharmaceutical company. And but in any case, it finally got to market, and it's currently used quite extensively for cancer treatment. But yeah, imagine finding this on an exam or something, starting with 4 carbons or less. It would not be very kind, would it? Okay, so before we finish up with ethers, does anybody have questions on anything that we've talked about from the ethers or epoxides? Okay, then let's go ahead and jump into our third and final chapter of Unit 2, and that is going to be looking at the aldehydes and ketones. So what's fundamental to the aldehyde and ketone as a functional group is the carbonyl. And what differentiates the aldehyde from the ketone is obviously where in the chain the carbonyl resides. So if you have an aldehyde, the carbonyl is always at the end of a chain. And if you have a ketone, the carbonyl is somewhere in the middle of a chain. Okay? So that's the only distinction. Now, I guess we can go ahead and do nomenclature first and get that out of the way. So we'll look at a couple examples of naming an aldehyde, and then we'll go to the ketone and wrap it up. So it turns out that with the aldehydes, nomenclature is really quite easy. So let me give you a quick example. Put a few So when you've got an aldehyde such as this, the reason I say they're pretty easy to handle is because, number one, carbonyl functional groups are always the high priority. So if we're looking at this, no matter what else is on here, I see a carbonyl, that means that's going to be my high priority group. I'm going to name it as an aldehyde. The second thing that makes these so easy is you never have to guess where to start numbering the chain, because you're always going to start numbering the aldehyde at the carbonyl, at that end. So when I start numbering, we'll number it down this way. And then just follow the normal rules of nomenclature. Alphabetize your substituents. So in this case, we've got the hydroxy, which I guess would go first. Then you've got the methyl group. And then this is a 7 chain, so we'll call that a heptan. And the suffix you're going to use to indicate aldehyde is simply Al. So we'll call it a 5-hydroxy-4-methyl-heptanal. Notice what we did not do here. We did not give the position of the aldehyde, because that would be redundant. Because we know that if you're dealing with an aldehyde and you're naming it as an aldehyde, the aldehyde is always at the 1 position. Okay? So we don't have to say heptan 1-al. The aldehyde position is assumed the 1. Okay? So let's look at another quick example. Let's do this one. So if we're looking kind of straight across, you have a 1, 2, 3, 4, 5, 6 carbon chain. See if we can get something better going the other direction. 1, 2, 3, 4, 5, 6. Oh, there's a 7 carbon chain. Which one is better? Which one is going to be our parent? Are we going to use the 6 or the 7 as the parent?
Don't you want to keep the double bond?
Oh, no,
Yeah, that's the thing you want to remember. Yes, we can get a longer chain by going this way, but remember, the rule is not simply the longest chain. The rule is the longest chain with the most functionality. So it's better to have a shorter chain that contains more elements of functionality than a longer chain that does not. So in this case, we would want to go straight across. So we're going to number this guy starting at the carbonyl straight across, like that. So that means we have that complex substituent at the 4 position. So let's see, that as a complex substituent, I think is going to be a 3-methyl is how it would begin. So that means we would number it like that. So that means we're going to start this name with the chlorine substituent. So we call it a 3-chloro, and then we'll do the complex substituent, which is at the 4 position of the parent. So that would become a 3-methyl butan 2-il. We're using the new style for complex substituents. And then that's a 6-carbon chain. We got the double bond at the 4. And that double bond would be, what is that? I think that is going to be an E. And then we just say enal. All right. Any questions on this one? All right, I want to look at one more example of the aldehyde with you because it gets a little bit different when you have them on a ring. So let's look at this. So if you've got the aldehyde on a ring, we're going to number around the ring so that the one position is given to the carbon that bears the carbonyl. So my one position on the ring is going to be that carbon. Once you've established that, you just follow the normal rules for rings. Right? You can go clockwise or counterclockwise. We would want to go so that we reach our the direction that's going to get to our first substituent first. So we would number around like this. So alphabetizing your substituents, you would have the fluoro going first. Then a 2,2 dimethyl. And to indicate that the aldehyde is on a ring, we're simply going to, it's kind of a mouthful, but you use the word cycloalkane carbaldehyde, where the ring size is substituted for alkane. So in this case, we'd say cyclohexane carbaldehyde. If it was a 5-member, we'd say cyclopentane carbaldehyde, etc. Like so. All right. Any questions there?
How come we didn't, oh, because the one always starts at the carbaldehyde?
Mhm.
Okay.
All right. So that is your aldehydes. Let's look at the ketones. The ketones are fairly similar. There's just one thing that's a little bit different. So let's say we did this one. So the difference between the aldehyde and the ketone is with the aldehyde, we always knew where the carbonyl was. It was always the one position. With a ketone, you don't, because theoretically, the ketone carbonyl can be anywhere within the chain. So that means you have to specify the location of the carbonyl, and you have to number the parent so that the carbonyl gets the lowest number. So start looking at this guy. It's going to be better for us to number this chain starting at the left because that gives the carbonyl the 2 position rather than starting at the right, which would give the carbonyl the 6th position, I think. So we number it like that. And then again, just do your substituents first. So we've got 4,5 dimethyl. That's a 7-carbon chain. A hept, double bond at 3, and that would be an E. Hept 3E. And now again, we have to give the position of the carbonyl because it could in theory be anywhere within the chain. So that's at the 2 position, and the suffix that we're going to use to denote the ketone is simply ONE. So 4,5-dimethyl hept 3E ene 2-one. So let's see an example where this is in a ring. So if you have a ketone that's present within a cyclo structure. So let's do this one. So here, we're always gonna start numbering at the carbonyl in a ring. So we would say the one position is there. And then you just follow the normal rules for rings. We could theoretically go clockwise or counter. In this case, you would get a 3-4 die substituted ring either way you go. So at that point, we have to go to the alphabet. So here, the ethyl comes before the nitro. So we'll number around like that. And just again, just arrange these alphabetically. So 3 ethyl, 4 nitro, and then we just call it cyclopentanone. All right. Notice with the ring, we don't have to give the position of the carbonyl, because you can choose to number the ring at whatever place you want. And so we're gonna always choose to start numbering the ring at the carbonyl. So when you have a ring ketone, you always know the carbonyl is the one position. All right? Any questions on this?
For the first example, if there was 2 ketones on it,
Mm-hmm.
would you just put like 2 and then the other place dione?
Yep, exactly.
And then for the second one, what if there were 2 ketones on that?
Then you would number around so that the 2 carbonyls had the lowest possible number. So you're always gonna have a 1 something dione, because you're always gonna start numbering at one of the carbonyls, and if you had another one, you would number around the ring to give it the lowest possible number.
Say that the ethyl was the other ketone, so it would be like cyclopentane dash 3 dione, or?
Yeah, mm-hmm,
Okay.
yep. But those are a little bit strange. You're probably not gonna see that very often. Okay, let's go ahead. One last example I wanna look at with you, because we haven't seen it quite yet. And that is, what happens if we had something like that. So in this example, we obviously have one of both. We have both the aldehyde and a ketone. So in a case like this, we have to figure out what has priority. So Danielle, you happen to have your handy sheet there. What does have priority? What's higher priority, the aldehyde or the ketone?
Aldehydes.
The aldehyde is. So that means we're gonna number this as an aldehyde, meaning starting over here, numbering like that. So what that means for us then is that we have to name the ketone as a substituent group. The ketone is a substituent of the aldehyde parent. And that's easy enough to do. If you have a ketone as a substituent, we just refer to it as an oxo group. So we would call this, I comes before O, so we'd start with the isopropyl. And then a 5-oxo. It's a 6-carbon chain. So we call it an oxohexanal. Any questions on that?
So if we had like 2 aldehydes, right, would it just follow the same rule as like ketones, where you would put hexane, the other aldehyde, di?
You wouldn't even have to give the number. It would just be like a hexan dial. Because,
Oh, they're
yeah, they have to be at the ends. Okay, then, oh yeah, go ahead.
And if you had 2 of the ketones, it would be a dioxo, or
Mhm.
how, does the DI and the I and the O go together like that?
Uh-huh, yep.
Okay.
Again, those are It's kind of weird. I honestly have not seen one of those where you would have, I mean, I've seen where you have two ketones in a molecule, but I've not seen where you have multiple ketones and an aldehyde in the same molecule. It'd be rather strange, but yeah, that's the way you would handle it.
It's more common to see like a dialone.
Mm-hmm. Yeah. Okay, then let's go ahead, now that we know how to name these, let's look, I want to look a little bit at the reactivity here with you. So if you're thinking about the carbonyl, compare it to like an alkene. So they're both carbons that are sp2 hybridized, meaning they have 3 hybrid sigma bonds and a pi bond, right? So that's kind of where the similarity ends. As you would probably expect, the carbonyl is a much more polarized bond, right? Because the oxygen is significantly more electronegative than carbon. And so, in fact, we can draw a second resonance structure for the carbonyl that looks like this. And this second resonance structure tells you pretty much everything you need to know about the reactivity of the carbonyl bond. Namely, that the carbonyl carbon is electropositive, and thus nucleophiles are attracted to it. And so what you're going to see, we'll kind of look at a generic mechanism in a second, but what you're going to see is over and over and over again, all we're going to do is just throw different nucleophiles at the carbonyl carbon and see how they attack, okay? But as a result of this much stronger bond polarity, it's a much stronger bond. And you already know this. You know this from just thinking about IR spectroscopy. So think about the IR spectrum of a carbonyl versus an alkene. Your typical alkene is somewhere between, depending on the nature of it, 1600 to 1650, versus a carbonyl, which is, again, depending on the exact nature of it, somewhere between 1700 and 1750. So it's a much stronger rigid bond than the alkene. So let's think about, before we get too far into the reactivity, let's look at the physical properties of these things. So if I have a series so let's do a series like this. So I think it's pretty obvious in this series of molecules, the yens, right? Obviously butane that only has London forces is probably going to have the lowest boiling point, right? On the other hand, the alcohol that has London forces, dipole-dipole, and H bonding should be the highest boiling of these. And that bears out. If you look up the boiling points of these things, butane has a boiling point somewhere between 0 and 1 degree Celsius. The alcohol is up at about 97 degrees Celsius. The question then is, what about the middle? Because the two middle structures that I've drawn, the ether, well, that has London and dipole-dipole. And then so does the ketone. So these two middle structures have the exact same types of intermolecular forces. However, the magnitude is not the same. Because of this dipolar resonance structure, this carbonyl bond is much more polarized than the carbon-oxygen bond of the ether. And as a result, you end up with significantly greater dipole-dipole forces. All right? So you can see this directly by looking at the boiling points of the two. The ether has a boiling point of about 8, whereas acetone boils up at 56, so multiple times higher than the ether, despite the fact that they have the same types of intermolecular forces. Okay. Okay, so let's look at some of the reactivity here. I told you a minute ago that what we're going to be seeing is over and over again nucleophiles attacking the carbonyl. So that's going to get us into a new style of mechanism. And this new mechanistic class that we'll see throughout this chapter is what's called nucleophilic addition. So in nucleophilic addition, I'm just going to kind of give you a generalized mechanism. We'll see plenty of specific examples later. But in this generalized mechanism, you're going to have a carbonyl, and you're going to have some nucleophile. And what we're going to see over and over is the nucleophile is going to be attracted to the carbonyl carbon and attack the carbonyl carbon. Again, because if you look at that resonance structure that we drew earlier, the carbonyl carbon has a partial positive charge. So the nucleophile comes in to attack. Well, we can't simply make a new bond from nucleophile to carbon. If we tried doing that, your carbon would have too many bonds. So as the nucleophile comes in to form a new bond with the carbon, one of the existing bonds must break. So what do you think is going to break?
Pi.
Yeah, the pi bond. The pi bond is weaker than a sigma bond, and so that's going to be the first one to break. So as the nucleophile comes into attack, that pi bond breaks. And that's going to give rise to what we very creatively refer to as the tetrahedral intermediate. All right, now, it would be a really great thing if we could somehow reform this carbonyl. Right, as I said, the carbonyl is a very strong bond. And so if you could get it back enthalpically, that would be a good thing for the reaction. So let's think about that. Let's think about maybe strategies we could use to get the carbonyl back. So obviously, in order to get the carbonyl back, we would have to bring electrons back down from the oxygen to the carbon to reform that pi bond. Well, if that's the case, that means we have to lose one of these existing groups, because the carbon can only have 4 bonds. So let's think about it in the context of an aldehyde. If you tried to do this with an aldehyde, we would bring electrons down, and that would mean losing H minus. How many times have you seen a hydride leaving group? Please say never, because they're really bad. So yeah, that's not going to work for us. Okay, well, what would be another option? Well, what if we were dealing with a ketone? If you're dealing with a ketone, then that means you would have to lose a carbanion leaving group. Is that any better? It's actually much worse. So the bottom line is, you really can't, you can't do it. I mean, I guess another option, a third option would be, could you reform the carbonyl and kick out the nucleophile? Yeah, that's kind of what, I mean, that would just get us back to where we started. So, the bottom line is, no, we can't reform the carbonyl, unfortunately. There is no leaving group to leave when you're dealing with an aldehyde or a ketone. So pretty much, you're stuck here at this tetrahedral intermediate. And generally speaking, the way this ends up resolving itself is you end up just protonating the O- under acidic workup. We'll see some variations on that theme as we start looking at the specific nucleophiles, but in general, the way this process is going to work over and over and over again is you're going to have a nucleophile come in to attack the carbonyl carbon, you generate a tetrahedral intermediate, and it stays there until you work it up under acidic conditions. All right. So, I want to spend just a minute before we leave this reactivity discussion to talk about the two ways in which we're going to see this work. With these addition reactions, we're going to see a slight variation depending on what kind of nucleophile we're using. So it's going to be a little bit different whether you are dealing with a strong nucleophile versus a weak nucleophile. This is very similar to this conversation that we had back with the ethers last week. So if you have a strong nucleophile, and we're going to use kind of the usual suspects. When I say strong nucleophile, I'm thinking about Grignard reagents, alkylithiums, alkoxides, hydroxide, H-, all your negative nucleophiles. So these things, remember, if you want a reaction, one reacting partner has to be strong. You either need a strong nucleophile or a strong electrophile. If you have a weak pair, that is not going to lead to a reaction. So with the strong nucleophiles, because the nucleophile is strong, you're good. So these reactions will occur uncatalyzed. You don't have to add anything to any kind of catalyst to this reaction because they'll happen by themselves because one of the reacting partners is strong, namely the nucleophile. With the weak nucleophiles, here, the electrophile is not terribly strong in the form of the carbonyl, and the nucleophile isn't terribly strong either. So these reactions will require catalysts. And again, when I say a weak nucleophile, I'm mostly talking about the neutral ones. So things like alcohols, water, those neutral nucleophiles. So whenever I say it's going to require catalyst, this can happen in one of two ways. You can either catalyze with acid or base. So you can use acid catalyst. What this is going to do, as we'll see, is simply it's going to make the electrophile stronger. Or you can use base catalyst. And this just does the opposite. Base catalyst will make the nucleophile stronger. Okay, but again, one of them has to be strong if you want a reaction. All right. So again, we'll see specific examples of this in just a minute when we start looking at specific reactions. But the last thing I want to mention with regards to the reactivity is, while we always lump aldehydes and ketones together, they are different functional groups, and they do have slightly different reactivities. So let's compare an aldehyde versus a ketone in terms of these nucleophilic addition reactions. Which do you think is more reactive here? Where the nucleophile has a choice to come in and attack the aldehyde or come in and attack the ketone. Which do you think it's going to happen more readily? Why would you say the ketone?
It's a secondary carbon.
I think the ketone's gonna spread the plus out more. Maybe?
Well, you're both onto something. You got the right ideas. There's two arguments to be made here. There's a steric argument and there's an electronic argument. So between those two, let's think sterics first. Which of those carbonyls is more available to attack? The aldehyde, right? Hydrogen is a whole lot smaller than an alkyl group. So sterically, the carbonyl of an aldehyde is much more available than the carbonyl of a ketone. Okay? So in terms of sterics, the aldehyde carbonyl is easier to attack. And again, simply put, a hydrogen is smaller than an alkyl group. Okay? Meaning that carbonyl is less congested. It's less hindered. All right? But there's also an electronic argument. Remember what we're relying on here for the nucleophile to attack. We're relying on the positive charge, or the partial positive charge, of the carbonyl carbon. So the larger the delta plus, on the carbonyl, the more reactive. Does that make sense? Remember, the whole source of reactivity here is that the carbonyl carbon, as a result of that resonance structure we can draw, has a delta plus. That's what's attracting the nucleophile. So the bigger the delta plus is, the more attracted the nucleophile will be to.
So the aldehyde will be more reactive electronically as well because there's less carbons to stabilize it then.
Yes,
So-
exactly. Remember, this kind of goes back to something we talked about in a different context in the last unit. What kind of groups are alkyl groups? Meaning electron donor groups, electron withdrawing groups? When we were doing all the benzene chemistry.
They're activators, right?
They're
So
activators.
donors.
Yep, exactly. Alkyl groups are, granted, they're weak donors, but they're still electron donor groups. So what that means is the alkyl groups are kind of pushing or donating electron density into the carbonyl inductively. Right? That was the definition of an electron donor group, right? Something that's pushing electron density into something. And so because the ketone has 2 electron donor groups versus the aldehyde, which is 1, what we can say is that the ketone has a smaller delta plus. Due to the 2 electron donor groups that it has. So again, there's 2 arguments that can be made, both point to the same thing, that the aldehyde is a more reactive carbonyl. Okay. Does anybody have questions on that?
So in the reaction, or if we have like a ketone and aldehyde on one compound, and then we introduce a nucleophile, right? It would attach to the ketone, that's what we're trying to get at?
Yeah, if,
I mean, attach to the
it would,
aldehyde.
yeah,
Okay.
and it, theoretically, it,
It's not 100%, right?
yeah, I mean, you should be able to get some selectivity. You typically have to control the reactions pretty tightly, run them very cold, things like that. But yeah, theoretically, you can get a difference in the reactivity based on the difference in electrophilicity. Okay, any other questions on this one?
So you said that you have to run cold, right?
Mm-hmm.
So is that also a reason, like, is the barrier or how much energy you need to attach the nucleophile lower for the aldehyde than it is for the ketone?
Yeah, yeah, exactly. Okay, so let's go ahead, I think that's all I wanted to tell you kind of in the generic sense in terms of the reactivity of these things. Let's switch gears a little bit and look at how you can synthesize these. And I think you know all of these reactions. We're just gonna kind of put them in one place. If I were to ask you to synthesize an aldehyde or a ketone, what pops to mind? What do you think would be the most common way of making an aldehyde or a ketone? Close. Yeah. Oxidation of an alcohol. Right? That is going to be by far the most common way these are made. It is most common, the easiest thing to do is just take an alcohol and oxidize it. Okay? So, depending on whether you're trying to make an aldehyde or a ketone is going to dictate what kind of alcohol you use. Right? So for instance, if you're trying to make an aldehyde, we have to start with a primary alcohol. And that also limits us in terms of what oxidizing agent we're going to use. So if we want an aldehyde, what do we have to use here?
PCC.
Yeah, exactly. You can't use those stronger oxidizing agents. You can't use permanganate or dichromate or the Jones reagent or anything like that, because all of those are fairly vigorous oxidizing conditions. And yeah, they'll make the aldehyde, but the problem is with those more vigorous oxidizing reagents, the aldehyde will ultimately get oxidized up to the carboxylic acid. So it won't stop at the aldehyde. So we have to use a weaker oxidizing agent, something like PCC. If you're trying to make a ketone, it really doesn't matter. So with the ketone, we're going to use a secondary alcohol, and you can use pretty much whatever you want. So that would include PCC, or we could use the Jones reagent. before. You could use dichromate. You could use bleach. A whole bunch of different things. Right? Now, just for the record, I should have put or between each of these, but when you go back to look at your notes, I'm sure you're aware you don't need all of these at the same time, right? Just pick one. All right? Any
Yes,
questions?
sir.
Yeah, go ahead.
What would happen if you just put all of those in at the same time?
That's a good question.
Would we get our explosion?
Yeah, possibly, yeah. I don't know, I've never really tried it, and I don't think I would either.
was just about to say.
But, yeah, so you just need the one. Okay, so, that is the easiest and most common way of making aldehydes and ketones, is simply through, oxidation of alcohols. Another way that you learned, I think last semester probably, was through the oxidative cleavage of alkenes. All right, so if you had something like, let's do that. You'll recall that there are a couple of different ways of doing this. There was the milder way, and then there was the more vigorous way. Does anybody remember what the milder way of doing this was? Yep, ozonolysis. So we're just gonna use ozone, and remember what this does is both of these conditions will take the double bond and cleave it. And all we do is we simply replace the carbon-carbon double bond with a carbon-oxygen double bond. So the product of the milder is gonna give you a ketone, and then the other half an aldehyde. So we get ketones and aldehydes. What was the more vigorous way of doing this?
Camino.
Yep, potassium permanganate. Concentrated and hot. And that's gonna do the same thing, almost. You're still taking the carbon-carbon double bond, replacing it with carbon-oxygen double bond. The only difference is that, so the left hand of the molecule is not gonna change. The only difference is that under those strongly oxidizing conditions, the aldehyde that you initially get gets oxidized up to the carboxylic acid. So instead of getting a ketone and aldehyde, we would get ketone and carboxylic acid. Okay. Any questions on this one? All right, a third way is one that we learned a little bit earlier this semester. This is a little bit of a specialized case because it's more for benzylic ketones, but we can make benzylic ketones and aldehydes through the acylation of benzene. And again, this is something that we did not too long ago, the Friedel-Crafts reactions. So if you wanted the ketone, just take benzene, using acyl halide and Lewis acid. You get that? So nothing new there. What if we wanted the aldehyde? that.
The.
Yep. The Gatterman cup. So he's carbon monoxide, HCl, copper salt, and the Lewis acid. Okay. So again, nothing new here. The last one is a little bit odd, and it's probably gonna test your memory. I know you learned this last semester, but you probably didn't do a whole lot with it. And that is through the oxidation of alkynes. So, if we have something like that, we have the option of either getting an aldehyde from this or a ketone. It's very similar, it's quite analogous to when you were trying to put a hydroxyl group on an alkene. When you try to do hydroxylation of alkenes, you can get Markovnikov or anti-Markovnikov addition, depending on the conditions you use. It's going to be very similar. You can imagine if you want to get an aldehyde, we would need an oxygen at the end, so that would be kind of a anti-Markovnikov addition. If you want a ketone, you need oxidation here, which would be kind of more of the Markovnikov addition of the oxygen. So, anybody remember? Let's do the Markovnikov. Let's do the ketone first. Anybody remember what those reagents were? Quite similar, actually, to the hydroxylation of the alkene.
Mercury compound.
Mm-hmm. It is a mercury.
I remember it was like slightly different.
And then you add water, I think.
Yep. So you typically use mercury sulfate and water.
But it's still the same thing.
And so if you remember the way this works, oops, no. So you would get that mercurinium ion, just like you did with the alkene reaction. And then water would come in to attack at the more substituted position. So really what you make is that. Does that look familiar? What do we call those?
The enol?
Yep, an enol. And can you isolate enols?
No.
No.
Let's change back.
Remember, the enols do that weird thing that we call tautomerization, where they form the more stable ketone. So that's how we can get a ketone from the alkyne. How can we get an aldehyde?
pH3.
No,
pHF.
it's a 9.
Yeah,
Oh.
you're on the right path. It is a boron reagent, but we don't usually use, I know when we were trying to do this with alkenes, we usually use BH3 for the hydroboration. We don't usually do that with the alkynes because you can actually get double addition with BH3. And so instead, we use a slightly different boron reagent.
Is it the 9-BBN?
That's one option, yep.
Silicon.
No, it's usually boron. So oh yeah, I think I know what you're going at.
I forgot what it
You can use 9-BBN, or the other one is dicyamylborane. And both of those require a step 2 where you use peroxide, basic peroxide. But what these are gonna do, if you remember how these go, they kind of make that 4-membered transition state. So I'm gonna draw out the dicyamylborane because 9 ppm is just obnoxious. So that's what, so the point is that both of these reagents are just big bulky boron reagents, ensuring that you don't get a double addition. That SIA stands for a secondary isoamyl, but that's just what those big alkyl groups are. But in the end, once you do the step 2 of this, the OH will replace the boron. So we ultimately get that. But there again, that's another enol. And enols don't hang around. They tautomerize to give you the carbonyl, in this case the aldehyde. Alright. Any questions here? Okay, so those are the, I think 4 different ways of making aldehydes and ketones, but as I mentioned a couple of times, by far the most common way of doing it is simply through oxidation of alcohols. Okay? All right, so let's go ahead, now that we've talked about the nomenclature, we've talked about reactivity, we've talked about the synthesis, let's start looking at reactions. It turns out aldehydes and ketones do a lot of chemistry. So you're probably, I would recommend kind of keeping up on these reactions. If you've got a running list, add them as we cover them, because by the end of the aldehyde ketone chapter, you're gonna have a lot of them. So, we'll start off simple. The first thing that we can do with these is hydration. So again, we're just going to be looking at different nucleophiles we can throw at the carbonyl carbon. The first of which, as you can probably guess with the name of hydration, the first nucleophile we're going to be using is water. So let's do, let's work with this. So I'm going to draw out kind of a, this first reaction just to kind of get a feel for what these reactions are going to look like. And then we probably need to modify it slightly. But in general, what we're going to see is just like that generalized mechanism that we saw a while back. The carbonyl carbon is electrophilic. You've got a nucleophile that is going to be attracted to it. So water could attack, and it would generate a tetrahedral intermediate. So as written, the mechanism would look like this. Now, at this point, there's a couple ways you could envision this mechanism. So some people like to do just a proton transfer. If you notice, this oxygen has too many protons, and this one doesn't have enough. So some people will draw their mechanism as just a simple proton transfer. This O- grabs that H, and everything ends up neutral. Alternatively, you can imagine solvent serving this role. You could have the O minus going to grab a proton from water, which would generate an hydroxide ion. And then that hydroxide ion, which is basic, could go grab a proton from here. And again, everything ends up neutral. So however you like to envision your mechanism, it's up to you. But in the end, everything ends up with its correct number of protons. I'm just going to draw it maybe like this. But in the end, we make a compound where the carbonyl is now has two OHs attached to it. And this is what's known as a hydrate. Or sometimes you'll see it called a geminal diol. Now, what do you think of this mechanism? How well do you think this would work? Do you think the way we're conducting this reaction would set up to give us a lot of the hydrate?
You need a catalyst or something?
Yeah, exactly. So remember what we were talking about a minute ago in terms of the generic reactivity of these things. A weak pairing is not a recipe for success. So you have the electrophile here, which is moderate. You have the nucleophile here, which is fairly weak. This is not really set up to do hydrate formation very well, because we have a weak pairing. So if we want this to go, we're gonna have to do something, right? We're gonna have to catalyze it. And we talked about those options, either acid catalyst to make the electrophile stronger, or base catalyst to make the nucleophile stronger. So let's just quickly go through and see how that's gonna change the mechanism. So we'll look first at acid catalyst. So what you're gonna see over and over and over again is that these reactions involving carbonyls and acid always start the same way. What do you think is going to happen?
Oxygen is gonna come from there.
Yeah, the whole point of adding the acid is that the carbonyl oxygen can go and grab it. And once it does, we make something like that if you follow the arrows. But remember, you can make a different resonance form of this, where you put the pi electrons onto oxygen, which would make the carbon a full positive charge. So you're going from the situation where it's neutral, where you have a delta plus, to the protonated form where it's a full plus. Right? This protonated carbonyl is much more electrophilic than the neutral form.
Can you please draw the resonance? I'm not.
Yeah, it's just breaking the pi bond and giving the electrons to the oxygen.
Okay.
So like that.
Thank you.
And actually, if you think about it, this is a better resonance structure than this one. right? Because the positive charge resides on a carbon here rather than the oxygen. Okay. So, once you've done that, once you've protonated, you've made a very good electrophile. And now the water, even though it's not a particularly great nucleophile, can come into attack. So we would get that. And then the only thing I have to do to make my hydrate is lose a proton here. And so in reality, what would happen is you would have water come in and grab that proton. So that does two things for you. It generates your hydrate, and it also reforms the acid catalyst. So if you think about it, we used H plus there, we got back H plus there. So it truly is a catalytic process. All right. Any questions on this one? Okay, let's see how this changes in base. Mechanisms are always easier in base. If you've ever got a choice between an acid catalyzed mechanism and a base, choose the base. Okay, so the way this is gonna change is instead of using H plus in water, we're gonna use OH minus in water. So you have to ask yourself, what's a better nucleophile, water or hydroxide? Any ideas? Yeah, negative nucleophiles are always stronger than neutral nucleophiles. So hydroxide's a much better nucleophile. It's going to attack first. That gives us that tetrahedral intermediate. Like that. And then this thing is just going to grab a proton from the water. So that gives me my hydrate, and it also regenerates that hydroxide catalyst. Used OH minus there, got back OH minus there. Any questions on this mechanism?
Which is faster, the acid or the base catalyzed?
The acid usually works a little bit better for these, but both can happen.
But they're both faster than the regular hydration.
Then the which one?
Than the regular hydration?
Oh, yeah, definitely. Uh-huh.
So what is it that's more desirable about the base catalyst? You said to use that if we have a choice,
Oh, I was just talking about writing mechanisms in general.
just on paper?
Yeah, on
Just 'cause
paper.
it's simpler?
Uh-huh, yeah. If you have two ways of doing a mechanism, one under acid, one under base, the base is always simpler. The one thing I want to call your attention to, though, and this is very, very general for all mechanisms. Notice your catalyst in the top. is H plus. Notice the charge of the intermediates. Plus is the charge on the catalyst. Intermediate is plus. Intermediate is plus. Then look at the base. Minus is the charge on the catalyst. Intermediate is minus. Well, that's the only intermediate you have. That is a very common theme in all mechanisms. The charge of your intermediates must match the charge of your catalyst. If you're ever doing an acid catalyzed mechanism and you get a negatively charged intermediate, like if you're working on an exam problem or something like that, and you're starting in base and you get a pot, or what did I say? If you're doing an acid catalyzed mechanism and you get a negatively charged intermediate, you're going the wrong direction. Your intermediates always must match the charge of the catalyst. All right. So, by the way, I mean, you kind of already know, we looked at the acid catalyzed version of this hydration and we looked at the base catalyzed version of the mechanism. But I didn't really need to tell you that this reaction wouldn't work well, because you do it all the time. Whenever you go into the lab and you clean your glassware, you're always mixing a ketone with water, right? You're rinsing everything with acetone. And when have you noticed a violent chemical reaction as a result? Never, because they don't react to a significant degree. So if you want water to react with your aldehyde or ketone to a significant degree, you've got to do something, i.e. catalyst. Okay? And that's true except under pretty much for every aldehyde or ketone except for the smallest. So if you have, let me show you this really quick example. This aldehyde is called chloral, and if you mix it with water, the equilibrium favors the hydrate. But that is by far the minority. You have to have very small aldehydes and very electron deficient aldehydes. And you make something that's called chloral hydrate, which coincidentally is used to knock people out. So I don't know if you've ever seen an old movie and they start dumping some liquid on a rag and then go up behind someone and put it in their face and they pass out. That's this stuff. So, but the vast majority of aldehydes and ketones definitely favor the carbonyl as opposed to the hydrate. All right.
Is that like a misconception on the chloroform, or is that two separate things?
Oh, that's two different things. So this is chloral. Chloroform is CHCl3. Yeah. Okay, so I think that's a good place to stop. So we'll pick it up there when we meet again on Monday.